Have you ever just stared at a really complex machine and thought, how on earth does that work? It looks like this crazy, complicated dance of parts. But what if I told you that underneath all that complexity, it's all based on a really simple set of rules? Well, today, we're going to pull back the curtain and deconstruct motion. We're going to learn the hidden language that all machines speak.
And we'll start with something you probably see every single day. Okay, so take a look at a car's windshield wiper. I mean, you've seen this a million times, right? There's a little motor under the hood that's just spinning and spinning in a simple circle. But somehow, that simple spinning motion gets translated into this perfect, smooth, back and forth sweep of the wiper blades. It's so predictable, so elegant, but how? How does that even happen? And that right there is the big question, isn't it? If we can answer that, we unlock the door to understanding pretty much every machine out there. But before we can dive in, we've got to make sure we're all speaking the same language.
Right. So first things first, let's get our terms straight. Is something a machine, a mechanism, or a structure? You might use these words interchangeably, but in engineering, they mean totally different things. So let's quickly break them down.
So first up, the mechanism. In our windshield wiper, that's a textbook example. A mechanism is basically a team of parts where if you move one part, the others are forced to move in a very specific, very predictable way. It's all about constraint. Its whole job, its entire purpose, is to take one kind of motion, like that spinning motor, and transform it into something else, like that perfect sweeping arc.
And what's so cool is that most of the mechanisms you see out there are just variations of a few basic patterns. It's like they're the fundamental recipes for motion. So here on the left, you've got a 4-bar mechanism. That's literally the heart of our windshield wiper. And on the right, that's a slider crank. You'll find that in basically every car engine, turning the up and down of the pistons into the spinning of the wheels. These are the building blocks.
Okay, so if that's a mechanism, then what's a machine? Well, a machine is kind of the next level up. It's when you take a bunch of mechanisms and put them together to do something useful. It's not just about changing motion anymore. It's about taking energy and turning it into actual work. A machine, you see, has a job to do.
Just look at this lathe, for example. This is a classic machine. It's got multiple mechanisms all working in concert. You've got one mechanism to spin the piece of metal, another one to move the cutting tool with incredible precision, and it's all powered by a motor. So it's taking electrical energy and turning it into the physical work of shaping steel. See? A bunch of mechanisms working together for one specific purpose.
All right, now let's talk about the complete opposite of a mechanism. Let's talk about a structure. A structure is a bunch of parts put together with one goal in mind, to not move at all. Its job is to take a beating, to resist forces, to handle heavy loads, and just stay put. We're talking pure, unadulterated strength and stability.
Think about a bridge, or the wooden trusses holding up the roof over your head. Yeah, they're made of tons of individual parts, but the entire design goal is to make sure there's absolutely zero movement between any of those parts. They're there to hold a load and be totally, completely rigid. That's it.
Okay, so we've got our big categories down. Machine, mechanism, structure. We know that mechanisms are like the recipes for motion. So, what are the ingredients? Let's zoom way in now and break this down to the most fundamental parts. Let's find the actual atoms of a mechanism.
All right, the most basic, fundamental piece of the puzzle is called a link, or if you want to get fancy, a kinematic link. Just think of it as any single part in the mechanism. The official definition calls it a resistant body, which is really just a technical way of saying it's strong enough to do its job, to push or pull without bending or breaking.
And believe it or not, these links actually come in a few different flavors. You've got your standard rigid link, right? Like a solid metal connecting rod in an engine. But you can also have flexible links. Think about a bike chain or a fan belt. They're designed to be flexible. And you can even have a fluid link, where the link is actually a liquid, like the brake fluid in your car that transmits the force from the pedal to the wheels. Now, we also group links by something really simple: how many places you can connect things to them. A basic link with 2 connection points, that's a binary link. If it has 3, it's a ternary link. 4, quaternary. And I know it sounds like a bunch of jargon, but trust me, knowing this is super important for figuring out how to piece them all together to create really cool, complex movements.
So, we've got our building blocks, our links. But a pile of links doesn't do anything, right? They're just parts. The real magic, the motion, happens when you start connecting them. And it's how you connect them that defines everything. Okay, so when you connect two links together in a way that controls how they can move relative to each other, you create what's called a kinematic pair. This is a huge idea. A pair isn't just two things touching, it's a connection that forces a very specific kind of movement. Think about a simple door hinge. That's a kinematic pair. It only lets the door swing. It can't slide up and down, it can't move side to side, it can only rotate. That's a constrained motion.
And we can even break down these pairs by how the links actually touch. If they connect over a whole surface area, like a piston sliding inside a cylinder, that's called a lower pair. These are super stable, really good for handling big forces. But if they only touch at a single point or along a line, like two gear teeth meshing together, that's a higher pair. These are what allow for more complex rolling and sliding motions.
And you can totally see the difference right here. Look at the left. Those are lower pairs. See how the block has a big surface sliding in the slot, where the shaft's spinning inside the hole? It's all about that broad contact. Now look at the right. Those gears, that's a classic higher pair. The only place they're touching is that tiny little line right where the teeth meet.
Okay, so what happens when we start stringing these links and pairs together? We get something called a kinematic chain. It's like we've assembled our Lego set. It's a complete loop, ready to move. But there's one last, absolutely critical step. To turn this floppy chain into a useful mechanism, you have to nail one of the links down. You have to fix it to something that doesn't move, like the frame of a car. The second you do that, bam! Suddenly, all the other links have a predictable path to follow.
All right, let's take a breath and zoom back out. We started with the big picture, the machine, and we've drilled all the way down to the tiny atoms of motion. Now we can finally put all those pieces together and see the entire map.
So, a chart like this, which probably looked like a bunch of intimidating engineering speak before, now it's just a map of our journey. We talked about mechanics of rigid bodies. Those are our links. We touched on dynamics, which is just the study of things in motion. And we spent most of our time in kinematics, the pure geometry of how things move. We've literally just walked a path right through the core concepts of mechanics.
So what's the big takeaway from all this? It's that the entire, seemingly complex universe of machines, it's all built from a super simple, super elegant toolkit. You got links, which are the parts. You connect them into pairs, which create controlled motion. You assemble the pairs into chains. And from those simple ingredients, literally every complex motion you can imagine is created.
And that's the real power here. From now on, when you see an excavator arm scooping up dirt, or you watch a bicycle's derailleur shift gears, or even just see your own windshield wipers, you're going to see it differently. You won't just see a machine doing a job. You'll see the hidden language. You'll see the links, the pairs, the kinematic chains working their magic right there in plain sight. So here's my challenge to you. What hidden mechanisms are you going to spot today?